I'm Jamie Watson from Niantic's R&D team. We introduced Footprints, a model to predict both visible and occluded surfaces given a single RGB image as input. Existing methods can estimate a segmentation of the visible walkable ground surface and an estimate of the depth to each pixel in the scene. Our Footprints model predicts two additional channels, both also pixel-aligned to the input image. Firstly, we predict the location of visible and hidden ground as it would be seen from the input camera. This allows us to identify free space in the scene and the untraversable footprints of objects. We also predict the depth to each ground pixel, hidden or visible, from the location of the input camera. Our image-to-image model predicts these four channels from a single colour image as input. Our model can produce plausible estimates of traversable ground, even in cluttered scenes. Hidden geometry could be represented in alternative ways. We could use voxels, but these can be slow and expensive. Amodal segmentation predicts the extent of objects, including their occluded parts. This would give the extent of the ground, but without predicting object footprints, which are crucial for obstacle avoidance. 3D bounding boxes give coarse object locations, but only for those of known classes. In contrast, we make lightweight per-frame predictions aligned to the input view. We could train our model from synthetic datasets, but these require substantial effort to create and still leave us needing to bridge a domain gap. Instead, our model allows us to train from real videos, for which depths and camera poses can be estimated. In our case, we estimate depths from stereo matching, and camera poses from OrbSlam. One frame from the video is selected as the target view. This is the training time input to the network. Nearby video frames act as source frames, which we use to form the hidden geometry learning signal. Each source image has depth and ground segmentation estimated. Pixels in a source image that have been identified as belonging to a traversable surface are then projected into 3D and back projected into the target view. This process is repeated from multiple source frames, and the predictions are aggregated to give us an estimate of the extent and geometry of the hidden surfaces. Learning from real data comes with its own challenges. When objects move in the training footage, geometry from the source view will not realistically be reprojected into the target view. To detect moving objects, we compute optical flow between our target frame and the previous frame in time. We separately compute the flow that would be induced in a static scene under the known camera motion. Pixels where optical flow differs from induced flow are inferred to be on moving objects and are ignored in the loss function. Evaluating hidden geometry is difficult, and few datasets exist for this task. We introduce a hand-labelled hidden ground annotation for each of the 697 frames in the Kitty Eigen test set. Each image has annotations setting out the extent of the hidden ground and the location of the base of each occluding object. Our estimates on Kitty are surprisingly good, considering this dataset was not designed for our task. Driving videos feature forward camera motion, while we favour training videos which view the same scene from multiple angles. Here, we show predictions from our model trained on our own handheld stereo dataset. These test sequences were recorded on a different day to the training data, filmed on a mobile phone. Again, we see how our model predicts object footprints and also free space, here estimating the continuation of the footpath around a corner. Please see our paper for quantitative results and ablations on Kitty, and results on the indoor Matterport dataset. We also demonstrate an application for our model, path planning. First, without our model, we see the result of path planning for an augmented reality agent using only the visible ground. Notice how the character must navigate purely in front of objects, as it has no concept of how far back they extend. Now, with our footprints model, the agent is free to move in a far more realistic fashion, travelling behind objects while still avoiding the ground that they're standing on. Thank you for watching.